Hello everyone, thank you for tuning into my presentation today for the Focused Ultrasound Foundation Symposium. My name is Andrew Drainville. I'm a postdoctoral fellow at Lab Tau in Lyon, France. The work I'm going to be presenting today examines the influence of bone properties on transcranial propagation and is a collaborative effort between researchers here at Lab Tau, as well as the Focused Ultrasound Foundation and the French Alternative Energies and Atomic Energy Commission. For accurate transcranial ultrasound treatment planning, the properties and geometry of individual patient skulls must be accounted for. This can be done through the use of clinical CT scans, which can provide both the geometry of a given skull and information that can be used to reconstruct the density, speed of sound, and attenuation of the skull. However, one of the current challenges when converting CT data into the relevant material properties is that there are a variety of different algorithms that can be used, with significant disagreement between them. And so, the goal of our project was to perform a parametric simulation study to examine the influence of bone properties on transcranial focusing. Our parametric study used a ray tracing model provided by the SIVA healthcare platform and a transducer based on the Insightec exablate transducer operating at 670 kHz. First, we quantify the effect of variation between the different conversion algorithms to obtain skull velocity, and then we look at how variation of independent parameters affected the focalization quality. To quantify the focalization error, we looked at the maximum acoustic amplitude obtained from simulations and the change in the position at which the maximum amplitude occurs. First, to examine how much the focalization quality is affected by the variation between different models relating the density and the acoustic velocity, we determined the maximum and minimum speed of sound predicted across all models at 5 different density values. We then performed simulations using these values for the skull, but with a transducer phase delay profile calculated based on the average velocity. And then we quantified the errors in the maximum amplitude and peak position relative to the results obtained from simulations using the average velocity. So it's hard to summarize all of the data here in 5 minutes, but on the left we can see that the uncertainty produces a maximum change in peak amplitude of 25% that increases at higher densities, and in the figure on the right we see that the position error remained below 2.5 millimeters for all results and below 1 millimeter for all but a single result, and again increased with increasing density. Next, we looked at how errors in estimated density affects focalization when the density is used as a parameter to estimate the acoustic velocity. So the transducer phase delay profile was calculated based on a skull density of 2,000 kilograms per cubic meter and a corresponding acoustic velocity of 2634 meters per second. And then the density was varied over a range of 20% without changing the transducer delay profile, while the individual skull velocity values were estimated based on each density value. Again, we quantify the focalization as a function of the relative change in peak amplitude on the left and the positional error on the right, with the dashed lines in each figure showing the values at which the transducer phase delay profile was calculated. There's an almost linear change in the peak amplitude as a function of density, though there is a slightly greater error when the density is underestimated. The positional error remains relatively low and is below 1.5 millimeters for all density values. Next, we looked at how changes in the longitudinal velocity would affect the focalization independent of all other parameters, with the velocity ranging from 2,000 to 3,600 meters per second using a phase delay profile based on an acoustic velocity of 2634 meters per second. This was done using 20 different velocity values and a longitudinal attenuation that was set to 0.477 decibels per millimeter. Here we can see the effect of changing velocity on amplitude and spatial position. Again, there is a higher sensitivity to underestimation of the skull velocity, leading to a maximum change in peak amplitude of about 40%, with the error in peak position changing by less than 1.5 millimeters for all values. Finally, we looked at how variation of the skull attenuation values, independent of all other material properties, would affect the focalization. We consider 26 values ranging from 0 to 1.5 decibels per millimeter, with the same density and acoustic velocity as in other simulations, and with a shear attenuation value that was estimated as twice the longitudinal attenuation. Based on our results, there is an exponential decay of the peak acoustic amplitude as a function of the attenuation coefficient, which is somewhat expected given the exponential nature of attenuation in the skull. We also found that there's almost no change in the location of the focal position relative to the geometric center of the transducer. And so to summarize the contributions of this work, we quantified the sensitivity of transcranial focusing to the existing uncertainty in derived skull properties based on a homogeneous ray tracing model. We did find that a solid model of the skull, which includes shear waves, was necessary to obtain accurate results, and we demonstrated how the parametric variation created more significant error in the maximum acoustic amplitude at the focus compared to the error in positioning. Some limitations of our work is that the conversion algorithms considered are generally intended for local property conversions, not average homogeneous skull properties. And so we expect that the variation of the average properties of the skull would be smaller than the ranges considered here, which may reduce overall sensitivity. We also did not consider skull heterogeneity, and we did not yet provide any comparison with experimental data. For further work, we would like to perform more simulations to examine the influence of bone heterogeneity in microarchitecture. We would also like to provide a comparison of simulation results with experimental data. We also plan to perform simulations that model the thermal dose at the focal point. Finally, I would like to acknowledge the organizations that generously supported and enable this work, and I'd like to thank you for your attention during my presentation. I look forward to answering any questions and seeing the other presentations during the rest of the Focused Ultrasound Foundation Conference. Thank you.